In this class, we have learned all different ways to integrate a function numerically, like the midpoint rule or the trapezoid rule or Simpson rule. What is the Monte Carlo integration? It is similarly a numerical integration, but instead of the previous two rules where we use grid to determine the integral, in Monte Carlo integration we use random numbers or random points to calculate the integration.
To understand the intuition behind a definite Monte Carlo integration, it is helpful to remember the way in which one calculates the average value y bar of a function f on an interval a to b, which is using this formula on the screen. It implies that if the average value of f on ab is known, then the integral of f can be computed by multiplying y bar with the interval length. But how is y bar calculated? So the law of large numbers ensures that by sampling a very large number of y values and taking their average, one can reach the true average value of f. So a simple version of Monte Carlo integration is exactly that, sampling a large number of points on a function within an interval, taking their average value and multiplying it by the interval length. And hooray, we've got a formula for Monte Carlo definite integration. For a demonstration, suppose one wants to find the following definite integral on the interval 0 to 1. First, a number of x values, say 200 x values, are sampled using a uniform distribution density function bounded by 0 and 1. You can see that the sampled x values are relatively evenly spaced from 0 to 1. Then, for every sampled x, we add fx to a cumulative sum, and finally we take the average. We know by analytical integration, the integral evaluates at pi over 2. From this chart, we see that the estimate gets very close to pi over 2 with 200 samples. The larger the sample size, the more accurate the approximation, so the narrower the 97.5% confidence interval becomes. But some questions still remain. What if the integral is indefinite? Are there any alternatives to uniform sampling? To answer these questions, we observe that a function f can be decomposed into the product of a p function and a g function, where the integral of p over a sample space bounded by a and b is 1. And in this case, p is called a probability density function, which can be used to instruct us how the x values should be sampled. We have this more general Monte Carlo integration method using importance sampling. After decomposing f into p and g, we get the average value of g by sampling a lot of x's using p, which is a probability density function. So for example, let's say we want to integrate the same f function we worked with, but from 0 to infinity. We observe that f can be decomposed into these two functions, one of which is a probability density function over the domain 0 to infinity. So we use this formula, which requires sampling a lot of x's from 0 to infinity using p, and get the average of all gx values. The sampled x points will be distributed like this, which corresponds to the shape of the probability density function. To compare this p function with the uniform distribution, we have these two graphs put together. So pause this video for a few seconds. Can you see the difference? And by the law of large numbers, the larger the sample size, the closer the estimate gets to the analytical solution, which is pi.
Monte Carlo integration is used to calculate integration equations that are too complex for rules such as trapezoidal rule and Simpson rule. For example, it is applied in estimating pi. This is achieved by calculating the ratio of the dots that fall within the circle against those falling in the area of a square circumscribing it. Some believe that the Monte Carlo is superior to the trapezoidal method and the Simpson method, given that the latter two involves drawing grids, which could leave out curved areas of a circle. In addition, it is useful to calculate volumes of large, complex three-dimensional objects where rules such as trapezoidal and Simpson are only optimal for two-dimensional objects. For instance, in physics, scientists need to identify the volumes of multidimensional graphs. Engineers who work at large simulation programs also use Monte Carlo integration to evaluate volumes of complicated shapes and objects. Monte Carlo integration is a non-deterministic statistical approach to approximating integrals. In engineering physics, Monte Carlo integration proves superior to other common numerical approaches such as the trapezium rule or the Simpson rule in cases where the integrands are either too geometrically complicated, highly dimensional, or indefinite.